I am very happy to be here with you all among old friends in a familiar home and with, most important, young, passionate students and postdocs to whom we must pass the baton. Because I don't know about George and Joel and others, but I'm getting tired, and we need some good young blood to keep tackling difficult problems. This problem, as I'll describe to you, has been around for 50 years. It'll be around for a lot longer. And even though I'm genetically predisposed to longevity since I'm Italian, I don't think I'll last that long. I think here we have mostly graduate students and postdocs in astrophysics, but I think we may have some particle physicists, some nuclear physicists, I'm not sure. So let me just, for a moment before I get in, take the big picture. I mean, we're trying to understand our place in the universe. We're trying to understand our universe per se. And so in order to do that, we have to understand the universe on all scales. So we have to understand the universe as a whole, cosmology, how the universe evolves as a whole. We have to understand the formation of galaxies, clusters of galaxies, clusters of clusters of galaxies, and the large-scale structure that permeates the universe. Joel spoke a lot to that particular scale and subject earlier. We have to understand the evolution of stars within those galaxies, so that's stellar birth, stellar life, stellar death, which will be the subject of my talk today. And ultimately, we have to understand the most exotic compact objects in the universe, neutron stars and black holes. Those scales are connected. I mean, you just saw from Joel's presentation, Joel referred to supernovae, stellar death, in the context of his work on galaxies. So they're all connected, and so it's very important to keep that in mind, because what Joel is doing, what I'm doing, what any of you ultimately do or will do, not only will it serve to advance the frontier within your own domain, but it will also serve to help advance the frontier across the universe. And ultimately, that's what's required to really understand things. You cannot understand any one phenomenon in a vacuum. That just won't work. So I'm going to talk about core collapse supernovae. So these are the death throes, rather violent death throes, of massive stars. So what's a massive star? It's a star that's 8 to 10 times the mass of the sun, more massive. And all such stars will die violent deaths in core collapse supernova events. Why are they important? Why do we care? Joel showed the periodic table earlier of elements, the building blocks of life as we know it. And core collapse supernovae are arguably the single most important source of elements in the universe. They are responsible for the dominant production of elements between oxygen and iron. So the oxygen you breathe, the calcium in your bones. And as you'll hear from experts like Young Chen, who will talk about the ARP process, they are believed responsible for half the elements heavier than iron. So there's no single source that's more important in the production of elements than core collapse supernovae. So let's talk about how, and why is my movie not running? There we go. So a massive star, as Joel mentioned, will evolve. It has a very fast life. It lives fast and it dies fast. And it kind of looks like what you see here, simplistically shown. It looks like an onion at the end of its life. It has an iron core that's roughly, as you can see from the left, this is drawn to scale, roughly an Earth-like object, except it's about 1.5 times the mass of the sun. So already, even at the beginning of this whole process, we're dealing with extremes of nature that are very different than what we have here on Earth. It's surrounded, the iron core is surrounded by a silicon shell, oxygen shell, carbon shell, helium shell, and ultimately a hydrogen envelope, and these things are rather large. You see here the outer envelope of the 15 solar mass star depicted is bigger than the orbit of the Earth around the sun. So if you were to put one of these stars where the sun is, it would envelop us and some other planets in the solar system. The iron core, this thing evolves for millions of years. The physics that I'll describe to you happens in a second. So once the process is initiated, the death of the star is rather rapid. The iron core at this point is what we call degenerate. It's cold. The energies in the system are much, much larger than the energies associated with the thermal component of the system. And the core is supported by degenerate relativistic electron pressure, which is a rather precarious situation. That's a metastable situation. During this time, you get what's called, under these conditions in this core, you get electron capture on protons and on nuclei. And electron capture removes electrons, which are supporting the core. And that is the primary destabilizing influence in getting the core collapse initiated. In addition, you also have some thermal dissociation of the nuclei in the core. When you dissociate a nucleus, you break it up, you lose thermal energy to do so. That is a less important destabilizing source, but it's still there. And the combination of those two things initiates stellar core collapse. So already you can see where the name core collapse supernova comes from. The core collapses, and the sound speed in the core is a function of density. We know the sound speed here on Earth is a function of density. The sound speed is a function of density, and the density decreases as you move away from the center. The infall velocity of the material in the infall increases as you move away from the center. So eventually you reach a crossing point where the infall velocity is larger than the sound speed. So the core splits into two pieces. An outer core, shown here in periwinkle, that's supersonic, and an inner core here, shown in purple, that's subsonic. Okay, and that's really quite important in what's about to happen. So that inner core, and I'll talk to you today about macroscopic physics first, and then tomorrow about the microscopic physics, focusing on the nuclear and weak interaction physics. So I will go through what I'm about to say in more detail tomorrow. But as the inner core collapses, you have nuclei in this core. The nuclei are becoming more neutron rich because of electron capture. An electron plus a proton gives a neutron plus an electron neutrino. They become more neutron rich, and therefore they grow in size, and they're coming closer together because it's being compressed, the material is being compressed. And eventually, the nuclei come together and everything merges into what we call a state of nuclear matter. So you can consider that purple ball as a large nucleus, the mass of about 3/4 the mass of the sun. Eventually, the collapse gets to a point where, owing to two factors, one, there's in the interaction potential of nucleon-nucleon interaction potential between protons and neutrons, neutrons and neutrons, there's a hard core. Basically, you cannot compress nucleons closer together because of that hard core. It's a repulsive potential. In addition, nucleons are fermions. They don't like to be in the same state. Those two factors ultimately cause that inner core to become incompressible, and it rebounds. It does so at what we call supernuclear densities. You're at supernuclear densities now. Those are densities in excess of the nucleons in the nucleus of an atom. Okay, so for symmetric nuclear matter, protons, equal number of protons and neutrons, a nuclear matter density is about 3×10⁻14 grams per cubic centimeter. Okay, and it varies with neutronization. So we're very, very high densities here. When that inner ball becomes incompressible, it rebounds, as I said, and it launches a shockwave, like a spherical piston, into the outer core. And that's very easy to see because the outer core is infalling supersonically. So any information about the rebound of the inner core cannot propagate out beyond that sonic point, the edge of the purple ball, faster than it's being swept in by the infall. It's like being on a treadmill. You're trying to walk and you're not going anywhere. So it's the same thing is happening here. And you have this outflow and this inflow, so you have a discontinuity in the flow. And that's a shock wave. Okay, so ultimately a shock wave forms because there is this sonic point, because of the incompressibility of nuclear matter under these extremes and the rebound of the inner core. That shock wave forms. It's the orange circle there in the diagram. And it will plow its way out of the iron core through the stellar layers and disrupt this star in a core collapse supernova event. Problem solved, right? I wish. Okay. So the problem begins there. It's plowing through, literally plowing through the iron core. You see here in yellow, you have material that's dissociated. So the nuclei are passing through the shock. The material is being compressed and heated. That's breaking up the nuclei, it's dissociating the nuclei, and you're losing energy doing that. And you lose about an explosion energy's worth of energy, 10 to the 51 ergs, canonical explosion energy, for every 1/10 of a solar mass you plow through. So that's already bad. But there's something that's even worse that has something to do with neutrinos. So during stellar core collapse, neutrinos, electron neutrinos, are produced. And I'll go through, when I go through the weak interactions, I'll show you the complete list. I'm just rattling off a few things here, but I'll show you the complete list. Electron neutrinos, largely, are produced during stellar core collapse. We'll get all three flavors and their antineutrinos in just a bit. But right now, we just have electron neutrinos largely forming during stellar core collapse by electron capture on the protons and the nuclei. Neutrinos are not social animals. They don't like to interact. They're passing through you and through us and through the Earth right now as we speak at unfathomable rates. But you're getting to densities in excess of 10 to the 11, 10 to the 12 grams per cubic centimeter and above. Under those conditions, the electron neutrinos actually become trapped. Amazing. It's really sort of what George always talks about, that supernovae, as you'll hear all this week, become laboratories for neutrinos because of the fact that these laboratories, the doors close and they're kept in, and you develop these degenerate seas of neutrinos in the stellar core. So the electron neutrinos become trapped, so they're trapped behind the shock wave. So the shock wave continues to propagate out, and eventually it reaches what we call the electron neutrinosphere. It's like the photosphere of the sun. It's the surface of last scattering of photons in the sun. Photons just escape at that point. When the shock wave passes the electron neutrinosphere, guess what happens? All of the electron neutrinos that are trapped from the production by electron capture are trapped in there, all of a sudden escape. And that's what I'll show you in the movie, which Bronson Messer is, produced. I'll show you in the movie that that's the real killer. That's the nail in the coffin. And that's what lays out the problem for us today. So that's the most enervating component of this and why the shock ultimately stalls. So we're going to be dealing with a stalled shock. And the fundamental question in supernova theory to date is, how is that stalled shock revived? Because, you know, if I want to make all the predictions associated with core collapse supernovae, the zeroth order prediction, as we say in Oak Ridge, is that they explode, you know? They explode from first principles, not parameterized, no dials. You don't get any dials, okay? And they explode robustly. So the explosion energies are commensurate with observations. At that point, you can then begin to think about predictions for nucleosynthesis. You can begin to think about all of the observables associated with supernovae, the neutrino signatures, the gravitational wave signatures. Christian Knott will be talking about the gravitational wave signatures today. Konstantin Yakunin is here from the Oak Ridge group, who's done a lot of work in that area. You first have to solve this problem, the explosion problem, before you can make first principles predictions for what all of these observables are in a supernova event. So here on the left, here on the right, your right, my left. You see here the formation of the shock wave, And initially, the shock, on top you have the velocity, on the bottom you have the electron fraction. So the electron fraction gives you a sense of the electron population, okay? And when electrons capture on protons, you reduce the electron fraction, okay? And when the neutrinos can escape, that reaction goes one way. It just goes toward reducing the electron fraction, producing neutrinos that then escape. So when you see the dip form in the electron fraction, right there, you'll see on the top, the velocity profile of the shock goes from having a velocity behind it that's positive, a velocity in front of it that's negative. That's indicative of a strong shock. It's actually reversing the infall of material. Now, shocks are funny things. You see there's a shock, and the velocity behind it is negative now, and in front of it is negative. So shocks move, in a peculiar way, sort of counterintuitive way. They're discontinuities in the flow, and how they move has to do with the jump conditions, which come out of the hydrodynamics equations. So it's not a trivial thing to predict how a shock will move. You might say, well, if the velocity behind it is positive, the shock will always move out in a positive way, or if the velocity behind it is negative, it'll always move in. But it moves out initially when the velocity behind it is negative, just because you've got all of this matter flowing through it for a while. And then eventually it stalls. It becomes stationary, and it slowly but surely recedes. And we have to, convert that situation to basically what you start with: positive velocity behind the shock moving out, because that's how you generate an explosion. Explosion means positive velocity behind the shock. So you can see here one more time, I'll let it run through after having annotated this thing to death. I want you to watch it, and you watch when the shock goes from being a strong shock to being a very much weakened shock. It continues to move out because of accretion through it, and then it eventually recedes. And correlate that with the electron fraction below. It's really remarkable. And so there's the story in a nutshell. Why things are laid out for us. Here we go. You have your shock. It's very positive and strong behind it. Already, it's weakened, continues to move outward. It continues to weaken. The velocity's behind it. The strength of the shock is indicated by the magnitude of the discontinuity. You see that the magnitude initially becomes very small. It weakens, and now, of course, it's strengthening just by virtue of its recession here, but not strong enough to move outward and to reverse the infall. Okay. All right, so that lays out the problem. So let me focus on the macrophysics of all of this. So, as I said, the big question is, how is the shock revived? And on the left, you have schematically what the situation is, and I'll show you in a little while. This gets much more complicated quickly. So you have the stalled supernova shock wave here. You have material flowing through it. The length of the arrows here are drawn to scale. They reflect the magnitude of the infall velocity. So material is decelerated as it comes through. You have the protoneutron star at the center. So that's the part of the core that is not shocked. And matter that settles, shock matter that settles onto that inner part. So that's the protoneutron star. And that'll go on to form a neutron star or a black hole. That protoneutron star, the surface of it is what we call the neutrino sphere. There are actually many such spheres, because the neutrino sphere is a function of neutrino energy as well as flavor. So that protoneutron star is radiating now electron, muon, and tau neutrinos and their antineutrino partners at a staggering rate of about 10 to the 52 ergs per second. But to put that, CGS is never quite does it for me in terms of impact. So that's 10 to the 45 watts. Okay, so you've got a neutrino bulb, 10 to the 45 watt neutrino bulb, radiating. Okay, and we'll talk about how that plays into this in a second. In between, you have this radius called the gain radius. Okay, and I'll talk about that in a second when I get into what is proposed as sort of the central paradigm by which the supernova shock wave is revived. Okay, so we've been at this for a while. Actually, in 2 years, it'll be 50 years from the seminal Colgate and White paper of 1966, which I'll show you in a second. And so there are 2, 4, 6, 7 ingredients that we know are important, relevant, some of them extremely important, some of them critical. Okay, and I'll show you which ones are absolutely critical today. So the first two are coupled. Gravity is the ultimate source of energy here, right? So when you have the gravitational binding energy of a neutron star that's going to be left behind after this star dies is 3 times 10 to the 53 ergs. The supernova energy is 10 to the 51 ergs. So the supernova energy is 1/300th of the available energy here. That's a good thing and a bad thing. It's a good thing because you have all of that available energy. It's a bad thing because that energy goes largely into the production of the neutrinos, which emanate from the protoneutron star over the course of a much longer time scale than the 1 second time scale that I'll talk about today in terms of initiating an explosion. So you can imagine from a modeling standpoint that if I have an energy source that's 300 times what I need, that I better model that very, very well in my models because I could very easily generate explosions artificially. Okay? So gravity provides the energy. That energy goes into neutrinos. I mean, you have matter that's infalling from the gravitational field. You gain kinetic and internal energy. Eventually, that stuff slams down on the surface. That kinetic energy goes into thermal energy. The thermal energy is radiated away in neutrinos. That's basically the conversion. And so those two factors are key. And Jim Wilson, again, I'll give you guys some key points in the literature to use as you after the summer schools. That way you can follow on for yourselves. Jim Wilson discovered that in the early 1980s that the shockwave can be revived by the absorption of electron neutrinos and antineutrinos on the protons and neutrons liberated behind the shockwave by dissociation. So the nuclei come in, they're compressed and heated, they dissociate, you've got now protons and neutrons around. The heating is mediated solely by the charge current nu-E bar absorption on protons and neutrons. And you can deposit enough energy to revive the supernova shockwave. This is what Jim Wilson discovered in the early 1980s. Jim was always way ahead of his time. And that basically, that neutrino heating mechanism, the delayed shock mechanism, the neutrino heating mechanism, different names for the same thing, that is the framework Jim Wilson laid out for us, and we still work within that framework. And really, since Jim, the problem has been to figure out how to get that to work, that neutrino heating mechanism to work. As I'll show you, the neutrinos alone can't do it. They need help from other things. Okay, what other things? Right now, everything I've shown you so far, the first schematic, this schematic, everything looks nice and spherically symmetric. Well, stars are not spherically symmetric, as you know, and certainly supernovae are not. So you have instabilities, fluid instabilities in the system. So you have instabilities in the protoneutron star. They can be quite exotic. You can have Ledoux convection, where you have both entropy and composition gradients. You can have what are called doubly diffusive instabilities. Jim Wilson talked about neutron fingers, which he actually needed to generate his explosions. Those result from a competition between hydrodynamic and radiation transport in the sense of neutrino effects, very, very complex instabilities. The bottom line is their role is simple if they occur. We don't find that they're particularly important. I don't think in modern simulations it's found that these are particularly important. Certainly for Jim they were. What their role is to basically dredge neutrinos up to the surface of the protoneutron star faster than they would get up by diffusion, because you're in very dense environment here, and you boost the neutrino luminosity. So you boost the neutrino heating. Much more important is what was discovered about a decade later, the neutrino-driven convection, as it's called. I mean, you have a heat source. You're heating fluid from below. So much like a pot of water on your stove, which convects, the fluid below the shock never be expelled, right? Because it will cool in the net sense and lose energy. It can never gain energy any longer. Now, later on, I'll show you that this gain surface is a rather complex surface, to say the least, even a not simply connected in a topological sense surface. But this captures the basic idea. So this neutrino-driven convection was discovered in the 1990s in the first two-dimensional simulations. Again, I'll point you to the literature on that by the Los Alamos group. Mark Harant, Willie Ben, Sterling Colgate, Rafe Hicks, Chris Fryer, and others all worked on those seminal papers that changed our game considerably. And it turns out, as I'll show you today, that's really quite important. That is a gravity neutrino heating and neutrino-driven convection are all critical components to explosions in massive stars. The fourth thing here, I won't show it to you in here, it's hard to show it to you here, is called the shock, up until this point, up until about 2003, actually, everyone considered the formation of the shock and the evolution of the shock, how it dynamically evolved. And nobody considered the stability of the shock. It turns out that the supernova shock wave is unstable to non-radial perturbations. If you perturb it radially, spherically symmetrically, it'll just ring and go back to where it was. But if you poke at it, you distort it from sphericity, those sphericities, asphericities, will grow. And this is known as the standing accretion shock instability, or SASI, okay? We have a standing accretion shock, and it is unstable, SASI, okay? And this was discovered in 2002, published in 2003. One important thing to note, because you'll hear this too in your careers, a lot of scientists believe that computation is like engineering, that you know everything, and it's just about the details. You put the numbers in, you turn the crank, and you get numbers out, 3.141592654, et cetera, right? Don't stand for that nonsense. The SASI was discovered computationally. There are discoveries that come computationally. In fact, I would argue, and you can argue, that the only way to understand a nonlinear universe is through computation, okay? And the SASI is a classic example of that in this context and in your field, in computational astrophysics. So I'll talk about the SASI in a little bit, but it turns out that the SASI acting, again, fundamentally changed the game. So we went from Jim Wilson, who discovered that neutrinos can, by heating the material, re-energize the shock, to the Los Alamos simulations that were the first 2D simulations and opened the door up to convection, which played a very important role in making this happen, to the SASI, which further changed the game. And unfortunately, these breakthroughs happen on decadal timescales. So we went from 82 to 92 to 2002-3, literally on decadal timescales. So such changes don't come that often, but we're fortunate enough to have accumulated enough of them now that, as I'll discuss later on in my presentations this week, progress on this problem is accelerating. It's been around for 50 years, but in the last decade, there's been a lot of movement, much more so than the first 40 years. Okay, nuclear burning. As soon as the shock wave gets out of the ion core, it will start burning the silicon, the oxygen, et cetera. Nuclear burning doesn't deposit a lot of energy for the shock, but it's very good at where it puts it, because your burning starts right ahead of the shock and behind the shock. So it's very localized to the shock region, and therefore the energy deposition is very, very efficient. And certainly it may play a very important role in marginal cases where you're marginally explosive. All right? And then, of course, stars rotate, just like the Earth and the sun. and stars have magnetic fields. Forgive my lack of artistic prowess. And those are the key ingredients that ultimately have to be included in the models. Today, I'm going to basically, rotation and magnetic fields will not be a major part of what I'll describe to you today, but they ultimately are there and have to be included in the models. But certainly the rest of it is there. So the stationary accretion shock instability. So on the top panel, in a 2D case, so 2D, we have a bad habit of referring to simulations as 1D, 2D, and 3D. As I'll show you in a second, these are really phase space problems. So they're higher dimensional than 1D, 2D, 3D. 1D is the spatial dimension. So spherically symmetric is 1D. That's just radius. Axisymmetric, r and theta, is 2D. So imagine on the top, you have basically a slice of a watermelon, and that watermelon is symmetric about this axis. So you get the picture on one slice, you have the whole 3D picture, okay? So you just need to solve for one slice. That's what I mean by axisymmetry, by 2D. And then, of course, 3D, game's wide open, no imposed symmetries. You're good luck, you're ready to go if you can do it. All right, so in the top, you see the SASI is a flip-flopping instability in 2D. It's an L=1 instability in the Legendre sense. And you see here, red indicates an upflow. So you have an upflow and a downflow and an upflow. It's basically flip-flopping about the equatorial plane here. Now, in 3D, it's much more complicated, and you'll see this as I show you some simulations later in 2D and in 3D. In 3D, there are two modes that are unstable, L=1 and M=1. There's a spiraling mode that comes in. So that's also very important, and it shows, too, why you ultimately, Mother Nature is 3D, not 2D. You have to move these models into 3D because when you move them into 3D, you open up entirely new degrees of freedom. So the M=1 mode does not exist in 2D, but it does in 3D, and it's like the L=1 mode, the other dominant unstable mode in the SASI. Dominant, by that I mean it doesn't saturate, it becomes nonlinear. Okay? Now, if I take my schematic and I superimpose the SASI on it at an instant of time, it might look something like that, where I have my protoneutron star radiating, I have my gain radius above it in dashed, and I have the shock wave in solid red. So the SASI is distorting the shock, and you can see some of the obvious benefits to the neutrino re-energizing of the shock. The SASI pushes the shock out to larger radius. The infall velocities at those larger radii are slower, so the material is moving through the shock more slowly and through the gain region more slowly, so there's more time to heat the material. The gain layer itself, the heating layer, is larger, and there are many other effects. And one of the most important things that you'll see in the movies when we get into the full-blown simulations that is critical with regard to the SASI, if you look here, you see where I have the cooling heating on the bottom and shock gain radius neutrinosphere on the top, those two large photons coming off of the protoneutron star. Let's call that the equatorial axis. What you'll see in the full-blown simulations is that the SASI sets up a geometry that causes large accretion funnels to come in quasi-equatorially in the 2D case. And those accretion funnels are massive, and they persist over very long periods of time. So the game is fundamentally different than when you have convective flow, which acts more locally. This is very much a global instability, which induces global changes in the accretion flow and induces sustained accretion over very long time periods. And in fact, that's one of the problems. When Jim Wilson obtained explosions invoking neutron fingers, his simulations were done by a half second after bounce, after stellar core bounce, 300 to 500 milliseconds after stellar core bounce. I'll show you in our simulations, we've carried them out to 1.4 seconds now, and they're still not done. So what I'll show is because of the SASI, success has come at a price. We can generate explosions now, but they unfold. They don't just happen. And that's really, that's fine. That's how nature writes it if we've got it right. But that's very taxing on the simulations, particularly in 3D, okay? All right, so I mentioned gravity. I always like to show this because this is, again, drawn to scale. This is based on our spherically symmetric general relativistic models. On the left, you have the schematic in the Newtonian case. On the right, you have the schematic in the general relativistic case. So the compactness of the situation is very different in the GR case, particularly when you get up to very massive stars like 25 solar mass and above. Even at 20, it looks like this. And for the relativistic aficionados here, you have the space-time metric here. Alpha is the lapse function. And you see a plot of the lapse function as you approach the center of the 25 solar mass star drops down to almost 0.75. So the proper time as seen by an observer there is 25% reduced relative to the proper time measured by an observer at infinity. Okay, so the clock is moving more slowly at the center than it is infinity already under these conditions. Okay, so Newtonian gravity simply doesn't cut it here. You have to do general relativistic gravity, or at least a good approximation thereof, but ultimately a full Einstein solution solve. So already you're talking about the hydrodynamics equations, the radiation transport equations for the production and transport and interaction of neutrinos, the Einstein system, and that's just the nuclear network, nuclear kinetics, right? And that's just the macroscopic physics. Then you have, of course, the full-blown equation of state physics, weak interaction physics that I'll talk about, underpinning all of this. So, in some senses, this is really one, I'd like to call this the mother of all applications because it has so much physics in it. Mike, who's left the room, once came up to me. We were at Granlabachen at a conference, and he came up and he said, "Tony, you have an impossible problem." That's an optimistic view. One of the things I wanted to do for you guys, I'm here with you for a few days this week and get a chance to talk about the supernova problem and can answer questions, as we mull around. But I wanted to give you, we've been here for 50 years. It's a big literature. So I wanted to give you handles into the literature so that you can go in, get other perspectives on the problem, get more details on the problem, and just kind of know where the key points are. So Colgate and White were the first to propose that neutrinos would drive supernova explosions. So our game starts here in 1966, and it's really a remarkable paper. 50 years ago, quasi, and Sterling, those of you who know him, was brilliant. We just lost him within the last 6 months. He was the one that first proposed this. It took about 20 years for Jim Wilson. There was a lot of work done in between, and some of that work is really pretty amazing. I'll show you. When we talk about the weak interactions, it's good to look at the supernova work from 66 on, because as many of you know, the electroweak theory of weak interactions, the Weinberg-Salam model, the standard model, was forged during that time period. In 1967, the Phys-Rev letter that Steve Weinberg received the Nobel Prize for was published. And I'll show you the abstracts of some of the papers from Jim and others in 1971, 75. It's a riot. It's just, you really see right there, that was a point when particle physics and astrophysics were like this. They were moving together like this. And this, of course, has continued to happen over the 50 years. It's happening now, as you'll hear from YU and Alex and George and others here, Young. You'll see that particle physics and astrophysics have remained like this. But it's just a riot to go back and look and watch this actually happening in the literature. It makes you feel like you were there. So Jim, 20 years later, as I said, discovered this. It was in 1982. He published it in Jones and Trella's volume. Jim was not one to publish a lot, certainly not a lot of journal papers. Hans Bethe kind of helped them along, and they worked together on the paper that's mostly cited for this development, Bethe and Wilson in '85. But it's important to know that Jim knew that this was the case from '82 on, and it was published first in Jones' volume, and then it was worked out in more detail by Hans Bethe and Jim Wilson. Yeah, please. Yes. And the equation of state. Yeah. Yes. Right. Yeah, I'm taking more of a macroscopic view, but yeah, yeah. Then 10 years after the fact, we had the first 2D models, as I mentioned, and then 10 years after the fact, the SASI discovery. And ultimately, those have all come together. These references here are references in which explosions, first principle explosions, are reported in the literature, okay, across a range of progenitor stars. So obviously, we can't just explode 8, 10 solar mass stars. We have to explode 20, 30, however it goes. This is a little bit simplistic in the sense, Kitawa et al., that's a 1D simulation. So here I say neutrino-driven explosions, most aided by convection in the SASI obtained across a range of progenitors. In Kitawa et al., it's a spherically symmetric simulation, but it's an 8 solar mass star. So in 8 to 10 range, it's the lowest, it's the oxygen, neon, magnesium core collapse supernovae. So in that case, you can actually generate a supernova explosion without multidimensional effects by neutrinos. But all of the others are in 2D or 3D. The Takiwaki et al. Is in 3D. All of the rest are in 2D. But it's also important to note that the physics in the models is not all the same. Burris et al., Marek and Janka, that's Max Planck. Mueller et al., Max Planck, and Oak Ridge, Bruin et al. They have general relativistic gravity, multi-frequency neutrino transport, all of that, the full physics in the models. Whereas Takiwaki et al., Su et al. Are Newtonian. And so those are, of course, precursors to simulations that must ultimately be done with some approximation to GR in them to see if the results still obtain. And there are other reductions in the physics there. Newtonian gravity just doesn't cut it. So those are interesting simulations, and we need to note them here because they are among those in which explosions are reported. But really, you need the full physics to be able to predict accurately what the outcomes are. So all of these things that I mentioned, neutrino heating, convection, and the SASI come together now in the last 5-7 years to give us a much better state of affairs than we had before. Getting explosions, supernova models, that was something that rarely happened. Jim had explosions and nobody else did for the longest time. And now we have a situation where multiple groups are obtaining explosions across multiple progenitors. That's really a first. That's a very different situation. And what's happening is, of course, we ultimately all will find ourselves hopefully in the right place where we're getting the right answers. What's happening is we're opening up our universe to 2D, to 3D, to these multidimensional effects, to the SASI, to the weak interaction physics is being improved, as I'll discuss, and all of that. There's been a lot that goes into these models that have put us in this better position. Okay, so what makes this problem so hard? Radiation. People have been doing computational fluid dynamics and magnetohydrodynamics for a long time. Much less has been done in radiation hydrodynamics, and for good reason. It's a higher dimensional problem. It's computationally very, very intensive, whether it's the supernova problem or other astrophysical radiation hydrodynamics problems. But it's a frontier. Astrophysical rad hydro is a frontier, and we need the baton to be picked up and carried forward in this application and others. So don't shy away from hard problems, because that's where a lot of the action is. So if I look to see why this problem is so hard, all I have to do is look as far as the neutrino heating rate. So the expression there in the box is the change in internal energy of the material due to neutrino absorption, and electron neutrino absorption and anti-neutrino absorption, 2 terms. So let's just look at one of them. It's a function of 3 quantities. So the neutrino luminosity, that's intuitively obvious. The more luminous the neutrino bulb, the more heating, all good. The second term, that's the really critical term. That's the square of the RMS energy. So the root mean square energy of the electron neutrinos, or antineutrinos, squared. Okay, so it depends on the neutrino spectra. So the harder the spectra, the more heating. Again, it's intuitive. But it's quadratic in the spectra, not linear. It's linear in the luminosity, quadratic in the spectra. And then finally, the 1 over F, it's the inverse flux factor. That's a measure of the isotropy or anisotropy of the neutrino radiation field. So if I pick a point, arbitrary point, boom, right there, at an instant of time, the neutrinos coming from the center are propagating. They're not all moving out radially. They're propagating in different directions. The more isotropic the distribution, the longer the neutrinos spend time in the gain radius, in the gain region, okay? The less isotropic, the less time they spend in there. So the less heating you have, okay? So the isotropy of the radiation field, as well as the spectra of the radiation field, are critical here. The only way to compute those fully, accurately, is to solve for the neutrino distribution function, F, which at an instant of time, at a 3D spatial location, r theta phi or xyz, whatever you like, you get the spectrum and the angular distribution of propagation of the neutrinos. So in 1 dimension, you just need theta p. Spherical symmetry tells you that once you know theta p, you've got everything. But in 2D and 3D, you need 2 angles, or equivalently 2 direction cosines, to uniquely specify a neutrino direction. So this is a phase space problem. There's space, there's momentum space, that's phase space. So this is 6 dimensions of phase space and time. So it's a 7-dimensional problem. Right there, you know, it's, you know, lasciate ogni speranza voi che entrate. You know, Dante put that over the gates of hell. Abandon all hope, ye who enter. You know, that's our inscription right there, okay? Hopefully we'll have time to talk about some of the mappings between physics and flops later in the week, or Bronson will cover that. To do this problem, you have to solve the kinetic equations for the distribution function F, the Boltzmann equations. You cannot solve such a problem with sufficient resolution except on a sustained exascale platform. So that's a 10 exaflop machine. Okay, so we cannot do that now. We won't be able to do it for a while. So you can't just stop and walk away. You have to keep going. So what's the next best thing? Well, if I integrate out the angular information, phi sub p, theta sub p, I cannot integrate out E, the energy, neutrino energy, the spectra. That's critical. That's quadratic in that dependence. So it's very important that I keep the spectral dependence. So let me start to integrate out the angular dependencies and keep the information about isotropy or anisotropy in the lowest order angular moments. So if I integrate over theta sub p and phi sub p, not weighted by a direction cosine, this is the energy density per frequency of neutrinos. Okay, so it's still spectral. I have the energy density. And then if I integrate and weight by a direction cosine, I have the components of the momentum density or the flux. So these are the 4 lowest order moments, angular moments, of the radiation field. So while I can't solve this problem, we can solve this problem. I mean, it's going to be a lot of computing time to solve this problem too, as I'll show you. But we can at least keep at this and do this. So here I'm keeping the angular information in a set of moments. I don't have all of the moments. There's an infinite hierarchy of such moments. I could keep going. I could weight this by Ni, Nj, et cetera, Ni, Nj, and K, et cetera, all the way up. It's an infinite hierarchy, so I'm losing some of the angular information, but not all of it. And hopefully I'm keeping the key angular information here, okay? So this is what we call multi-frequency treatment, which is really entry-level realism for core collapse supernova modeling. And ultimately, multi-frequency must give rise to multi-frequency, multi-angle at some point down the road on your time scale, not our time scale so much, okay? So that's how we move. So what do I mean by such treatments? You'll hear me say things like multi-group flux-limited diffusion and multi-group variable editing factors and multi-group variable editing tensors, yada, 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 okay? It's ultimately all of that. Those are different multi-frequency treatments, different ways of working with the lowest order angular moments. Okay, so in the multi-group flux-limited diffusion approximation, and here I'm showing the case of spherical symmetry just for simplicity, I integrate the Boltzmann equation, shown in brackets there, partial f with respect to t equals, over mu. Mu is cosine theta p. Okay, and in 1D in spherical symmetry, that's all the angular information you need. And I get an equation for psi naught. Psi naught is the energy per frequency. I showed it as capital E before, but it's the same. And that's the definition of psi naught. It's the lowest order, 0th order angular moment. Psi 1 is the first angular moment. It's the momentum density, or flux, per frequency. Okay? Now, the problem is it's in the dots on the right. The dots on the right include psi 2 and psi 3. But you're not solving for psi 2 and psi 3. You're solving only for psi 0 and psi 1. So you have a closure problem. You have more unknowns than you have equations. And you have to close the system of equations. And whether it's multi-group flux-limited diffusion or variable Eddington factor tensor methods, it's really about expressing psi 2 in terms of psi 1 and psi 0, or psi 3, or psi 4. Actually, in 2 and 3D, you have quite a large number of moments. So you have to express those psi 2, psi 3, et cetera, in terms of psi 0. That relationship is the closure relationship, okay? So let's see how it works in flux-limited diffusion. And it's very important. This is a technical detail, but it's so important to the problem and so important to you all gauging, you know, the quality of the solution to the problem, that it's important that we go through this. If I use multi-group flux-limited diffusion, this is what I say. I say that psi 1 is related to psi 0. This is a closure at the level of psi 0. So I'm going to just basically evolve psi 0. And I'm going to relate psi 1 to psi 0. So this is a closure at the lowest possible level. I'll show you a higher order closure in a second. So if I relate psi 1 to psi 0 in this way, and I call capital lambda the following, let's see what happens in the limits. We know that deep down in the star, the neutrinos have to obey Fick's law of diffusion, okay? And we know far out, when the mean free path is large, the neutrinos are going to stream radially outward. So we've got those two limits, and we've got to join those two limits together. So in the limit that the mean free path is very large, so the neutrinos are streaming, this term drops out. If I use this piece, I plug in for lambda, I get Fick's law. Psi 1 is simply minus lambda over 3. So the flux is given by the gradient of the energy density related by the mean free path. Okay, that's Fick's law. On the other hand, if the mean free path goes to 0, so now the neutrinos are strongly interacting in the center, the mean free paths are small compared to the system, they're diffusive. This term dominates. Okay, and when I plug that in, oh, sorry, I did it the other way around. When the mean free path goes, when the mean free path goes to infinite, this drops out, and this is what we get. My apologies. Okay, it becomes free streaming when the mean free path becomes infinite. This drops out, you plug this in, the gradients cancel, and you have simply psi 1 is psi 0. That's free streaming. When lambda goes to 0, you should have diffusion. fact, this dominates, this goes away. If I plug that in here, then you get obviously Fick's law. That's flux limited diffusion. Now, there are different ways to do this. You can get flux limited diffusion. I mean, this seems very simplistic, this patching, but it works a lot better than it deserves to work. And it's an art to tailor this. And you can actually tailor this so in spherical symmetry, you can match Boltzmann. So this is not to be taken lightly, but certainly it gives you a view of how we begin to do this if we can only do spectral treatments without full angular information, okay? That's multi-root flux limited diffusion. If I go to variable Eddington factor tensor methods, then of course I'm not truncating at psi 1. That is, I'm going to keep both the psi 0 and the psi 1 equations, both of them, and evolve for the energy density and the momentum densities. Then I need to close at higher order. I need to relate psi 2, psi 3, et cetera, to psi 0. Those are, you can't write those down so simply, generally. So let me just talk about the different approaches that you can take. First is what we call a prescribed closure or an analytic closure. That's where you have an analytical expression that relates psi 2 to psi 0, okay? And you close the system because you have an analytic expression. But you don't always have that. So an example of that is what's called maximum entropy closure. And in maximum entropy closure in 1D, you have such an analytic expression for the closure prescription. It was first developed by Chernohorsky and Boltzmann in '94, and if you look at that paper, you'll see an example of that. But generally, you don't have that, or those are not, they're good, but they're not good enough. At the end of the day, you have to do something much more sophisticated, and you have to begin to compute your closures. So you can have maximum entropy closure in 2D and 3D, which involves a separate computation, okay, independent of the equations you're solving, all right? The next level up is actually to take the Boltzmann equation and approximate it, simplify it, and solve an approximate Boltzmann equation for an approximate F distribution function. If you have F, then you can compute any moments you want. So you can therefore close the system. But remember, it's an approximate F. It's not a full-blown Boltzmann solution. And then ultimately, you can use moments approaches, these approaches, a moments method, a spectral method, in conjunction with a Boltzmann solve. They can be solved together. Now, we can't solve this, of course, now. But down the road, you could, and they can be used together, and one can accelerate the convergence of solution for both systems of equations by working them together. So these are 4 approaches to closing your system of equations for your radiation moments, your angular moments, okay? All right, so George, should I, in a few minutes? Yeah, stop it now? Okay, okay. Yeah, let's stop. Let's stop. Perfect, I'll continue this, we'll just keep going tomorrow.
Lambda sub 0 A. So you said later that lambda is the mean free path. So lambda sub 0 is like what your lowest order mean free path or something?
Yeah. You know, do you remember what lambda sub 0 A is? It's a bunch of constants.
Oh, okay. Okay. Oh, okay.
It's just right. It's part right. Yeah, it's just a number. Thanks, man. Yeah. Yeah. Yeah, actually, that's a very good point and a very interesting question because we're ongoing now in trying to understand, uh, when the SASI is critically important and how it is important as a function of progenitor mass. Uh, it seems as though the more massive the progenitor, the more critical it is, and the more dominant it is in the evolution. As you go to lower progenitors, uh, things become more dominated by neutrino-driven convection, and we're all trying to understand exactly why that happens, because it's a competition of timescales. There are convective timescales for the development of convection, and the SASI has its own timescale longer for its development, as you know, and those two timescales are operative, and they are, or typically longer. They're impacted by the conditions, the compactness of the progenitor star that you start with. Good question, Austin. So these are both Oak Ridge guys. You'd think we'd never see each other. So I think there's something that we're not going to be able to alter fundamentally, and that is that, and I'll get into this hopefully later this week. When you solve the Boltzmann equation, or for that matter, the moment equations, you cannot do so in a time explicit numerical sense. You have to do so either in a fully time implicit or at least partially time implicit sense, or semi-implicit, semi-explicit sense. Okay. The collision term, the neutrino matter interaction term, okay, the right-hand side of the Boltzmann equation, the source term, cannot be handled explicitly. It has to be handled implicitly. It's too stiff, if you will, for it to be handled explicitly. Once you accept that fact, and I don't think that's going to change in the next decade, once you accept that fact, then the sustained exascale applies, because when I make that back of the envelope computation for what is needed, all I'm using are the flop count associated with preconditioning, just the preconditioning part of the linear system that results from the treatment of the collision term implicitly. Not the solution or other parts of this, it's a lower limit. So if you just look at the raw number of flops, and even smart algorithms with, that go like n squared rather than n cubed, you're basically dealing with, for the Boltzmann case, a sustained exascale to do a simulation in any reasonable amount of time. And that's at, the resolution there is limited too. It's not poor, but it's not the kind of resolution folks like to use, for example, when they do turbulence or they do pure hydro simulations, where they go to 10 to the 3 cubed number of grid points. I mean, you just with all this physics, you cannot get beyond 500 adaptive radial points and hundreds of angles. I mean, in space. I mean, you're just not. You're going to be of order 10 to the 2, of order 500 cubed. And so that's modest resolution, and even with that, it's just impossible. So it's a very good question. We are moving toward, as you know, semi-implicit versus fully implicit methods, but the collision term has to be handled, and that's what dictates the computation term.
I think we better stop here. So we'll take a 15-minute break and be back at 11:30, and then Alex Friedland will continue this discussion, but talking about neutrino flavor. Thanks a lot, Tony.
Thank you.